David. And so I'm very happy to be invited and get this opportunity to talk about this. This has been an ongoing activity for some time, and I will get into the history and so on and our development. But I organized, I was part of a panel debate that we had in December with really great participation, even from the European Commission and the Swedish Parliament, Hannes Schöller, a leading journalist, and so on, and about more than 50 people from KTH, for example, from ECS. And there is going to be a follow-up panel debate in March, organized by the Young Academy of Sweden. And this seminar can be seen as a connection to the really good and interesting Digital Futures activity at KTH. So I think it's a natural connection here, and I will have some discussion related to that. And to introduce myself a little bit, and I will try to keep the presentation and the discussion at a quite high, accessible and pedagogical level. And please don't hesitate to ask and maybe technical details. This can be something, so please email me afterwards if you're interested in that. But I think this issue, and in general what we call this digital math, this is relevant for everyone, for everyone in society. And to get an overview, I will show a trailer that we developed for our approach to Digimath, online education to schools. So there it will be an accessible.
Digital math is the future. Super important for industry and society, and based on the scientific method. Old math is often hard to comprehend, and many find it boring and pointless. This makes people really bad in math, while our society is in great need of math and programming. The solution to this problem is digital math. Digital math is creative, has a clear purpose, and the possibilities are unlimited. We are therefore offering Digimath, an online program for learning digital math from preschool to top academic and pro. We are a team of leading scientists in mathematics and pedagogy, as well as creators and artists. The program combines physics-based games with learning abstract concepts, such as algorithms. The learning activities involves music and visual art as part of the pedagogical concept. We also want to break through stereotypes about math and programming and reach everybody, no matter age, gender, or background. So, this is my dad. He also wants to say something.
In my vision, digital math is the automation of society based on the scientific method. People interact with exciting simulations predicting reality, such as new airplanes, new medicines, and new sustainable food for the future. People see, test, and edit the open math source code underlying the simulations. Our predictive simulations reach the highest level of society and industry. By just learning a few basic algorithms, anyone can understand and carry out such simulations. And in our program, it takes just a few months.
Great talk, Dad. So the math education hasn't changed in 300 years. Join the revolution and support our project.
Okay, so I hope for those of you who are not intimately familiar with our activities, for example, this gives an overview of sort of the general ideas and concepts. And now I will go
to the more concrete problem at hand. So the problem of reproducibility in science has now been raised at the sort of the highest level in several different places. And I think the Karolinska president, Ottersen, describes the problem concisely. So he says like this, we are in the midst of what some have called a research reproducibility crisis. While scientific discovery and complexity are developing at an unprecedented speed, less than 50% of scientific research studies can be reliably replicated. Left unchecked, this troubling fact may threaten our ability to generate sound evidence-based knowledge that meets society's needs. It's time to look beyond the traditional measure of quality and re-examine the very concept of quality itself. So this is almost an apocalyptic description of a development that in principle has already happened. And there are several people highlighting this problem in a similar way. Hannes Kjöller, a leading journalist in Sweden, and Lorena Barba, together with the National Academies of Sciences in the United States. And I will emphasize here that what I am focusing on is solutions, digital solutions. So I will come to that, but I will also emphasize that if we don't do this, don't act, don't sort of develop this to solve this urgent problem, that is what Ottersen is describing. The situation is not good today. And that's a very pedagogic illustration that this is not a sort of a very narrow issue, that in school, one may not only give the answer to a problem. So if a student gets a math problem and just writes the answer, like 42, then the teacher will say, show your work. You have to show that you sort of, the derivation, where did the answer come from? But in research, this is often not possible to see or reproduce how the answer was derived or constructed. So in principle, it is more like it can be almost, to be a little bit provocative, like a story with illustrations, like here are some interesting results. Okay, I want to get into them, I want to reproduce them, but that is not possible from a paper, typically. And why is this so? So then, but there are solutions, and I will specifically emphasize here. So, and you could say I have been driving this development already since 2003, even though the problem statement was not as urgent then. So I, together with colleagues, started an open source project called Phoenix for automatically solving advanced mathematical models, where you only give the sort of mathematical notation, the mathematical source code, just a few lines. And then based on this, everything is automatically generated and solved. And I see this as a component in the solution. And this has also been sort of very well disseminated and tested. So you can describe this as a de facto world standard now for advanced mathematical modeling. And I'm leading the largest online course in Sweden. So there have been over 30,000 participants. So many thousands have sort of worked with this online in a web browser. So this is really a functional solution for advanced mathematical model. And in the United States, there are now guidelines for requiring the publication of the digital objects. So this is a report from the US National Academies of Sciences, where the work was led by Lorena Barba, who was also in the panel debate. So this was already 3 years ago. This was sort of presented in that setting of a solution, that to publish the digital objects, and we are showing that with these platforms, that is certainly possible. And Lorena Barba also describes this then. What we are calling for is changing the norms to give importance to the full set of digital objects that are part of a scientific study, and acknowledging that the scientific paper is insufficient today in its method section to include all of the information needed for another researcher to confirm the results or build from those results. So to just have this story with illustrations, it is not enough to satisfy the scientific method. So instead, these digital objects and what we call this digital math. So you have the math source code, the math formulation. This would satisfy that. And again, to be a bit provocative, the technology to achieve this has been available since even the 80s and 90s. So then it was possible to, for example, log in to another scientist's computer system and inspect simulations, inspect computations, runs computations. And now this can be presented in what we say like a one-click solution even, or you have just a few lines that you're editing sort of in a very easy, accessible way. And what we mean by what do we mean by digital math, and how does this connect to science, to the scientific method? So we say that the digital math framework can be presented as the foundation for modern science based on constructive digital mathematical computation. And the perspective is that a computed result, for example, an array, a coefficient vector, and in our setting, we focus on finite element method, a function, a solution to a differential equation, a plot. This is a mathematical theorem, and the mathematical open source code and the computation, and in our setting, in this Phoenix framework, is the mathematical proof. So then you have the connection to the scientific method, that you have a falsifiable theorem, and you have the full derivation, the full proof. And what I can present are that this unlocks, for example, some of the grand challenges in aerodynamics, turbulence, biomedicine, and so on. And also we connect this to education. So this, which I will come back to. Yes, this gives understandable. Again, a very perspective of some of the core elements, digital math. So automated discretization. So given an input of the mathematical notation of a mathematical model. So here is just one line. It can be just a few lines for an advanced mathematical model. Then with the finite element method as a systematization of the solution, automatization of the solution. This can be, the low-level source code can be automatically generated in our open source Phoenix framework. So hundreds of thousands of lines of low-level source code, which is not something that a human can develop in a sort of robust way. So one principle is that in every 1,000 lines of source code, there's a human error, for example. But here you just have a few lines, 1 to 10 lines perhaps, which a human or a group of humans can really check. This is really the model, the formulation of the model that we intend. And the rest is automatically generated. And this also means that for a reviewer, someone who wants to reproduce, they only have to inspect these few lines. So this can take minutes, whereas inspecting these hundreds of thousands of lines is not realistic. Another aspect is automated error control. So this means in a mathematical model to compute solutions, you make an approximation. and then to be able to say something, to have a reliable prediction or solution, you need you have a condition on the error. So here we require the error in a certain output to be below a tolerance. In this framework, then we can then automatically generate a discretization and approximation to satisfy that condition on the error. So this means that you can have a predictive solution, and these two together then allow sort of that you give a mathematical model as input, as high-level input, and you automatically compute solutions. And the only thing you have to inspect is the model, and at lower levels, that the method for computing this adaptive error control is in a similar way described in this high-level mathematical notation. So all new scientific artifacts are described in this way and can be published together with the digital objects. This was recently also picked up by the European Commission. So now it is very relevant with Horizon Europe. This is the platform for science in Europe. And the European Commission then published a report on reproducibility of scientific results in the EU from the Directorate General for Research and Innovation. And in a similar way as the other quotes I highlighted, they describe this, that there is in this way. Second, there is a perceived deliberateness or at least carelessness in scientific production due to competitive pressures. So a growing proportion of scientists are perceived as willingly or unwillingly bending some of the basic premises of the scientific method to produce fast science or even make-believe science. Facts and theories that are declared true but are dubious or even false. This rests more on the structure of incentives of science making embedded in culture and practice than on deliberate attempts to cheat. The need for results to be reproducible and the tangible steps needed to make them so may help results be trustworthy and keep scientists honest. So the EU spends an enormous budget, so all the populations are expecting, as Hannes Schöller is highlighting, the scientific community to use these budgets to produce sort of science-based results with which society can build on. And today this is described as it is not functioning as intended. But to push for this reproducibility can sort of change the direction to a constructive setting, back to a scientific setting. And the European Commission are describing possible remedies, sharing of data, protocols, materials, software codes, and other tools underlying publications, transparency of analysis and modeling. So this is the publication of digital objects that I was mentioning, and the digital math setting that we're describing. And possible actions then. For example, that the Horizon Europe encourage and support reproducibility and to police guidelines and to fund this sort of development, supporting frameworks. And I will describe, so how do we, I described that the technology has been available. I described a framework. Now I add another ingredient, ubiquitous computing. So for this to be, these aims to be, to have impact and to function, there needs to be a critical mass, many people involved in this, many people reviewing, many people being able to interact. And this is possible today. So this is, as I described, in these online courses, thousands of participants have done this. And in our communities, this is pervasive. So one technology is Jupyter, and it's available in, for example, Google Colab, where a virtual machine is provided by Google. There are many other similar solutions, MyBinder, for example. So this means that in a web browser, anyone can run and reproduce. So it means it's not only a few scientists, a few people in the field who can do this, but this is something that everyone can do. And it's scalable. So this is what I mean by the ubiquitous. So in principle, billions of people could do this. And the second aspect of ubiquitous computing for more a little bit more specialized needs, for more a little bit more advanced users. There are virtual machines where you have a universal computing environment. So regardless of the virtual machine, it's the same environment. And there you can have single nodes, for example, single machines, which with a shared memory with hundreds of cores. And this can also is now realized in a distributed computing setting. We have verified that with thousands of processors. So also for large scale computing, this is available. And this is how it can look, that as you saw before a little bit, the mathematical formulation notation, and you have plots in the same document in the web browser. In our activity, we generated impact. As I say, a large online course based on this, the digital math. My team has been elected to IVA, Royal Swedish Academy of Engineering Sciences, the 100 list. Pilot project with one of the top Formula 1 teams, and invited seminar with top engineers at Boeing. So there is sort of high interest in the industry and traction. And in Sweden, we are participating with predictive aerodynamics for electric aircraft in the ELISE project. This has been highlighted by the Swedish Prime Minister. NASA highlighting especially this adaptive error control. They say they want the whole field to go in this direction. And in benchmarking workshops where I've presented, I have been the only one presenting those type of results in that setting. So really driving the field forward. And now invited to the World Expo together with Vinnova. And several high impact Horizon 2020 projects and so on in this direction. Good feedback from students. And now, which I think is fantastic, also then widen the initiative to the education initiative to the general population, to schools. And with a leading municipality in Sweden, we have been making sort of established a large project with great feedback. And then you can say, okay, there must be large sort of technical problems. Why sort of let's do this, but what do we need to solve? But there do not appear to be open problems to achieve pervasive reproducibility. So with the technology I'm describing, this is possible, and this is being done in some settings. And as I said, to be a little bit provocative, this has been available since the 80s and 90s. And specific technology then, for example, Jupyter has become a sort of standard for this, where you can run, sort of edit Python in a web browser and run that anyone can do. And in general, virtual machines where you have a universal environment. So this is already available, and we are demonstrating general advanced applications, frameworks in this. So a discussion. I open the discussion now to everyone, and please ask specific questions. So what is going on now is a collaboration with the European Commission Open Science Unit. So they have been part of a previous panel debate. They see this as extremely interesting, important, and want to go in this direction as I described. So this is something that you or everyone should participate in, I think. And I think there is an urgent need for new publication frameworks based on these digital objects. So that's something, an activity that we also can contribute to. So one idea that has been raised in Digital Futures here is so archive has become a kind of a standard for traditional paper publication. So to make a similar framework as that, together with reproducibility, so with the digital objects. So that's something that, in principle, we already have realizations of. That's something we can highlight. And then please go and see on our digital math website the panel debate with the Swedish Parliament. It was recorded, so it's available there. There are some discussions available, and also now in the upcoming in March with the Young Academy of Sweden and Swedish Parliament, a follow-up debate. Yes, so please, that's I open the discussion now.